In August 1984, a haunting and unexplained tragedy unfolded in a secluded region of Cameroon in Central Africa. Lake Monoun, a quiet, bone-shaped body of water nestled amid farmland and a small rural village, had long been an unassuming presence in the local landscape. Situated far from cities or notable landmarks, the lake was largely unknown to the outside world, but one fateful night transformed this tranquil setting into the site of a chilling scientific mystery. At approximately 11:30 in the evening, residents living near Lake Monoun were startled by an unusual, deep rumbling. It passed without much concern at first, but something unimaginable had already begun. A cloud, dense, white and unnatural, suddenly erupted from the surface of the lake and crept silently over the nearby road. By dawn, the strange mist still lingered, cloaking the area like an eerie veil. Locals, rising for work and unaware of the danger, passed through the cloud as they followed their usual path along the road. Tragically, those who entered the fog found themselves unable to breathe. Within seconds they collapsed, suffocating in silence. By mid-morning, winds finally dispersed the deadly mist, but it had already claimed 37 lives. Victims were found sprawled across the road, slumped in vehicles, on motorcycles and on foot, many having no idea they had walked into their final moments. Panic and confusion followed. Initial theories ranged from folklore-driven fears to geopolitical suspicions. Some villagers whispered of a cursed lake haunted by malevolent spirits. The Cameroonian government, grasping for answers, suspected a chemical attack, perhaps a plot by terrorists or insurgents. But this explanation soon unravelled. No rebel group claimed responsibility, and the location, a remote road in a sparsely populated area, made no strategic sense for a targeted attack. Moreover, the complexity of acquiring and deploying chemical weapons cast doubt on the theory altogether. Attention soon shifted toward a possible natural origin. Geologists noted that Lake Monoun lies along the Cameroon volcanic line, a chain of ancient volcanoes stretching from the Gulf of Guinea deep into the African interior. Though the volcano beneath the lake had been considered dormant, scientists questioned whether it could have reawakened in some subtle but deadly form. To find answers, the US Embassy in Cameroon invited Dr. Haraldur Sigurdsson, a renowned volcanologist and geochemist from the University of Rhode Island. Months after the event, he arrived at Lake Monoun to investigate. Despite exhaustive testing, Sigurdsson found no evidence of a typical volcanic eruption. The lake bed showed no signs of disruption. There were no sulfur compounds that would suggest magma-related gases, and the water temperature remained unchanged. No thermal spike, no boiling, no explosion. Instead, what made this event so terrifying was its silence and invisibility. The killer had left no obvious scars, only the lifeless bodies of unsuspecting villagers and a mystery that science was still struggling to decode. The breakthrough came unexpectedly when a bottle containing a water sample from deep within Lake Monoun was brought to the surface. As it emerged, the cap burst off with the force of a shaken soda can. For geochemist Haraldur Sigurdsson, this peculiar event was the key. The water from the lake's depths was found to be saturated with dissolved carbon dioxide, CO2, much like a massive pressurized reservoir of carbonated water. The implications were chilling. In the aftermath of the lake's mysterious tragedy, where 37 individuals had perished in what witnesses described as a sudden, silent cloud, Sigurdsson began to connect the dots. He realized that every symptom aligned with carbon dioxide asphyxiation. As a gas, CO2 is colorless, odorless, and significantly denser than air, traits that allow it to linger close to the ground and overwhelm anyone caught within its reach. The survivors' accounts made it evident. They hadn't seen or smelled anything unusual. But the gas had been lethal all the same. Driven by this revelation, Sigurdsson spent the next 2 years developing a detailed theory. He proposed that Lake Monoun was not merely a tranquil tropical body of water, but a rare and hazardous geological phenomenon. According to his findings, magma beneath the lake bed had been releasing CO2 for generations, perhaps even centuries. This gas rose slowly through cracks in the crust, dissolving into the lake's deepest, coldest waters, where it stayed, trapped beneath a lighter, warmer surface layer. In most lakes, seasonal temperature shifts cause natural mixing that prevents such gas accumulation. Winter typically cools the surface water, making it denser and causes it to sink, forcing deeper water upward. The opposite happens in warmer months, creating a constant overturn. But Lake Monoun lies near the equator, where the climate remains warm year-round. Without seasonal variation, the lake's stratified layers remain stable and unmixed, allowing gas-rich bottom waters to stagnate over time. In such conditions, the lower layers can quietly and gradually accumulate enormous quantities of dissolved CO2. Sigurdsson theorized that the warm upper layer acted like a cork on a pressurized bottle. If that cork were disturbed by a landslide, seismic tremor, or even the buildup of gas reaching a critical threshold, it could trigger a sudden, violent overturn. The result? A catastrophic release of gas in an explosive event known today as a limnic eruption. Sigurdsson's chilling conclusion was that Lake Monoun had been a geological time bomb, accumulating lethal gas in silence and secrecy for centuries, its true nature invisible to those living around it. In 1986, 2 years after the fatal event, he submitted his research to the journal Science. It was rejected as implausible. His theory, though rigorously formulated, remained confined to academic obscurity, known only to a few within his scientific circle. But obscurity wouldn't last long. Just 100 kilometers northwest of Lake Monoun sat another, even more dangerous lake, Lake Nyos. It too was unknowingly primed with vast amounts of dissolved CO2, and it too was teetering on the edge of catastrophe, one that would soon unfold with devastating consequences, proving Sigurdsson's once-dismissed theory to be all too real. As twilight descended over the remote hills of Cameroon on the evening of August 21, 1986, the villages surrounding Lake Nyos lay in serene silence, their residents already settling in for the night. Around 9 in the evening, a deep rumbling noise broke the stillness, an ominous sound eerily similar to one reported before the tragedy at Lake Monoun just 2 years earlier. Yet, in these isolated communities, few grasped the magnitude of the catastrophe about to unfold. Without warning, a colossal release of carbon dioxide, estimated at around 1 cubic kilometre or roughly 300,000 tons, erupted from the depths of Lake Nyos. The gas burst forth with immense force, reaching speeds close to 100 kilometers per hour before collapsing under its own weight. Being denser than air, the CO2 did not rise, but instead hugged the ground, cascading into the valleys and sweeping through the surrounding villages in a suffocating, invisible tide. What followed was an apocalyptic event, unlike anything the region or the world had witnessed. The eruption unleashed a towering 25-metre wave, likely triggered by the sudden gas displacement that crashed against the lake's shore. As the white heavy mist flowed outward, it extinguished nearly all life in its path, reaching as far as 25 kilometres from the lake's edge. In the villages of Nyos and Char, only 4 individuals survived, saved by the fortune of being on elevated terrain. Some residents were rendered unconscious rather than killed outright, only to awaken over a day later to scenes of unspeakable horror, their families lifeless, their communities silent and still. Survivors bore not only the psychological scars, but also lasting physical ailments, respiratory damage, skin lesions, and even paralysis. The toxic cloud had left no distinction between human and animal. An estimated 3,500 livestock also perished, their bodies strewn across the valleys alongside the fallen villagers. In the days that followed, those who ventured into the disaster zone described a chilling, unnatural silence. No birds chirped, no flies buzzed. Even the insects had succumbed to the gas, leaving a landscape eerily devoid of sound or motion. The waters of Lake Nyos, once calm and blue, had turned a haunting shade of blood red, resembling oxidized iron. The transformation lent an almost mythic sense of dread to an already unthinkable tragedy, a localized extinction, sudden and merciless. This devastating event claimed the lives of 1,746 people, nearly 50 times more than the Lake Monoun disaster. Its scale and surreal nature drew immediate global attention. Scientists, geologists, and emergency teams from across the world descended upon the area, urgently working to understand the forces at play. In doing so, the world began to consider more seriously the theory that had only recently been proposed, that certain crater lakes in volcanic regions could silently accumulate vast amounts of CO2, which, under the right conditions, could be violently released. Lake Nyos, like Lake Monoun, was found to be a rare geological phenomenon, a tropical lake resting atop a volcanic hotbed with deep, stratified layers. Over centuries, carbon dioxide had silently seeped in through underground springs, saturating the cold bottom waters in increasingly dangerous concentrations. The 1986 eruption was a catastrophic release of that trapped gas, turning a peaceful lake into the epicenter of one of the deadliest natural gas disasters in recorded history. A delicate balance existed within the lake, a warm, lighter layer of water floating atop a denser, colder layer saturated with dissolved carbon dioxide. This upper layer acted like a cork, trapping the gas below with deadly potential. The precise trigger of the catastrophic 1986 event that suffocated nearly 1,800 people remains uncertain. However, the prevailing scientific explanation suggests that a sudden landslide, perhaps a cascade of boulders tumbling from a nearby cliff, may have pierced the lake's fragile stratification. This disturbance could have allowed the CO2-rich bottom waters to rise rapidly, causing the gas to erupt violently at the surface and unleash a suffocating cloud across nearby villages. Eyewitnesses who survived recalled hearing an ominous rumbling or crashing noise moments before the fog of death arrived, lending credence to the landslide hypothesis. Later observations by scientists did in fact reveal signs of a recent rockfall on the lake's perimeter. Other plausible scenarios have also been proposed. A sudden drop in ambient temperature could have cooled the lake's surface, destabilizing its thermal layers and prompting the same catastrophic upwelling. Similarly, a forceful wind or a heavy rainfall could have churned the surface waters enough to trigger a gas release. Though the precise cause remains a subject of debate, the Lake Nyos tragedy provided haunting validation of a theory once dismissed as improbable. Sigurdsson's proposal of a limnic eruption, a deadly natural hazard previously thought to be myth. Upon their arrival, researchers made a startling discovery. The eruption had not emptied the lake of its accumulated CO2. The same was true for Lake Monoun, which had experienced a smaller but similar eruption 2 years earlier in 1984. In both cases, dangerous levels of gas continued to accumulate in the lower depths, creating the potential for another explosion, possibly even more devastating than the last. Faced with this ongoing threat, scientists debated a range of possible interventions, some bold, some bizarre. One plan proposed dispersing lime into the lakes from helicopters to neutralize the gas chemically. Another involved detonating explosives to force the gas out in one massive release. A third envisioned digging underground tunnels to drain the gas-saturated waters, but each idea was ultimately deemed too costly, dangerous, or impractical. Instead, a more elegant and low-tech solution emerged. In 2001, a team of engineers installed a floating platform on Lake Nyos, connected to a pipe reaching deep into the lake's bottom. By channeling the CO2-rich water to the surface, the gas could escape gradually and safely in a controlled, geyser-like manner, essentially mimicking a miniature, harmless limnic eruption. Over time, more pipes were added to accelerate the process. By 2009, Lake Monoun was considered safely degassed, and by 2019, Lake Nyos followed suit. Yet even as those two lakes were rendered safe, attention shifted to a third, even more ominous threat. Another deep lake in equatorial Africa was found to harbour the same treacherous conditions, a potential limnic eruption waiting to happen, but on an even grander scale. The environmental recipe for such disasters is exceedingly rare. They occur only in specific tropical regions where volcanic or tectonic activity underlies deep lakes. These lakes must be located at relatively moderate elevations that still allow cooler temperatures and must be deep enough to maintain stable, stratified layers of water that remain largely undisturbed. When all these factors align, what appears to be a tranquil lake may in fact be one of the most lethal natural time bombs on Earth. Only one other lake on Earth has ever been identified as being at risk of a limnic eruption since the 1980s, Lake Kivu, straddling the borders of Rwanda and the Democratic Republic of the Congo in East Africa. Unlike the smaller and more isolated Lake Nyos and Lake Monoun in Cameroon, Lake Kivu is a massive, complex body of water nestled within the tectonically volatile East African Rift Valley. Here, immense geological forces are gradually pulling the African continent apart, slowly shaping a future ocean basin. This rifting activity has thinned the Earth's crust, triggering significant volcanic activity beneath the lake that vents carbon dioxide through hydrothermal springs into its deeper, colder waters. In terms of sheer size, Lake Kivu dwarfs both Nyos and Monoun. While Lake Nyos is just 1.7 kilometers long and 1.5 kilometers wide with a depth of 213 meters, Lake Kivu spans more than 88 kilometers in length and 48 kilometers in width, plunging to depths of 475 meters. This colossal scale makes Lake Kivu not only more massive but also potentially far deadlier. Much like its Cameroonian counterparts, Lake Kivu is stratified into distinct layers of water, with the colder, denser bottom layers saturated in dissolved gases, primarily carbon dioxide and, crucially, methane. These lower layers are capped by a lighter, warmer surface layer that acts like the cork on a pressurized bottle, preventing the gases from escaping. The separation between these layers is strikingly thin, often no more than a few centimeters, and due to the lake's location in equatorial Africa, where the climate is perpetually warm, there is little to no seasonal mixing between them. This thermal stability traps the gases below, allowing them to accumulate year after year, unchecked for centuries. What makes Lake Kivu uniquely perilous is the addition of methane gas. Methane is not only far less soluble in water than carbon dioxide, making it quicker to reach dangerous saturation levels, but it is also highly flammable. Microbial activity at the lake's depths, driven by organic-rich sediments, constantly produces methane as microorganisms break down material in the oxygen-starved bottom waters. Furthermore, the same volcanic systems that feed CO2 into the lake may also inject methane directly from below, compounding the danger. This volatile combination means that if Lake Kivu were ever to experience a limnic eruption, the consequences could be catastrophic on a scale never before witnessed. An eruption would not only release a massive cloud of asphyxiating carbon dioxide, as was seen at Lake Nyos, but could also unleash ignitable methane, potentially turning the gas cloud into a blazing inferno. The resulting catastrophe could suffocate and burn everything in its path. Several natural triggers could provoke such an event. The gas-rich layers might eventually reach a critical threshold of saturation, causing any additional gas to instantly convert into its gaseous form and rise violently to the surface. Alternatively, a strong enough kinetic disturbance, such as an earthquake or volcanic tremor, could disrupt the fragile stratification of the lake, mixing the layers and rapidly depressurizing the deeper waters. This would force the dissolved gases out of solution all at once, causing a massive release. While a single landslide might not be sufficient to destabilize a lake of this magnitude, more powerful geological forces certainly could. In a seismically active zone like the East African Rift, earthquakes ranging from magnitude 4 to 6 on the Richter scale are common. Any one of these tremors, if occurring in the wrong place at the wrong time, could be the catalyst for an unprecedented disaster, a limnic eruption of immense scale that would imperil countless lives in the densely populated regions surrounding Lake Kivu. Seismic events continue to rattle the regions surrounding the East African Rift, and even though they aren't constant, powerful earthquakes still occur. In 2008, a magnitude 5.9 earthquake struck the western shores of Lake Kivu. Just 3 years earlier, a stronger magnitude 6.8 quake hit near Lake Tanganyika, close to the border between the Democratic Republic of the Congo, DRC, and Tanzania. Going back further to 1990, a more intense magnitude 7.2 earthquake was recorded near modern-day Juba, the capital of South Sudan. If a sufficiently strong earthquake were to occur in the vicinity of Lake Kivu, it could agitate the lake's stratified layers, potentially triggering the release of vast quantities of gas trapped deep beneath its surface. This scenario mirrors what occurred at Lake Nyos in 1986, where an explosive release of carbon dioxide killed over 1,700 people. However, the threat posed by Lake Kivu is significantly more alarming. Not only could a seismic event cause this potential disaster, but an extreme regional drought followed by sudden heavy rains might also destabilize the lake's delicate balance. If the water levels drop dramatically, the stability of the lake's layers could be compromised, increasing the risk of a limnic eruption. As climate change accelerates and extreme weather patterns become more frequent, this possibility becomes even more concerning. The true danger of Lake Kivu lies not just in its potential to erupt, but in the unimaginable scale of destruction it could unleash. During the 1986 Lake Nyos disaster, approximately 1 cubic kilometre of CO2 was released. Lake Kivu, by contrast, is estimated to contain around 3,000 cubic kilometres of dissolved carbon dioxide and another 60 cubic kilometres of dissolved methane. This translates to roughly 2.66 gigatons of CO2, a quantity equivalent to about 5% of the world's total annual greenhouse gas emissions, released not over a year, but in mere hours, all in one location. What makes this situation even more catastrophic is the population density around Lake Kivu. Unlike the isolated communities near Lake Nyos and Lake Monoun, the shores of Lake Kivu are home to approximately 2 million people. The cities of Bukavu and Goma, both major urban centres, lie directly along its western shoreline. If Lake Kivu were to erupt in a limnic event, the death toll could be unprecedented, potentially becoming the deadliest natural disaster in human history. Despite the looming danger, scientists remain divided over whether Lake Kivu has experienced similar eruptions in the past. Sediment analysis reveals 9 brown layers, hinting at historical mixing events, yet interpretations vary widely. Some researchers argue there's no clear evidence of a large-scale limnic eruption in the past 12,000 years. Others believe that one such event may have occurred around 4,000 years ago, suggesting the lake might already have a volatile past hidden beneath its calm surface. There's also ongoing debate about the immediacy of the risk. A 2005 study by environmental scientists Martin Schmid and Michael Halbwachs, both experts on Lake Kivu, indicated that methane concentrations in the lake's lower layers had increased by approximately 15% since 1975. If that rate of accumulation continued, the lake could reach full methane saturation by 2090, potentially resulting in a catastrophic eruption. However, a later study published in 2020, co-authored by Schmid himself, claimed that no measurable increase in methane levels had occurred after all. But even this newer study has sparked controversy. Critics argue that a lack of detectable change does not necessarily prove stability. It may simply mean that current detection methods are insufficient. Efforts to render Lake Kivu safe have been proposed, drawing from lessons learned at Lake Nyos and Lake Monoun, where degassing tubes now help reduce the buildup of gas. However, the challenge with Lake Kivu lies in its sheer size and complexity. Its massive volume and greater depth mean that safeguarding the lake would demand an enormously larger scale of intervention technologically, financially, and logistically. And as the debate continues, and the region grows more vulnerable to both climate impacts and tectonic activity, the silent threat lurking beneath Lake Kivu remains one of the most terrifying natural time bombs on Earth. Lake Kivu, unlike the similarly volatile lakes in Cameroon, sits at the heart of a highly unstable geopolitical region. Its western shores lie within the Democratic Republic of the Congo, DRC, though much of this territory no longer operates under the authority of the national government. Instead, it is dominated by armed rebel groups, most notably the M23 militia, a well-organized faction that has reportedly received military support from neighboring Rwanda. In recent years, M23 fighters have seized control of key urban centers like Goma and Bukavu, the largest cities along the lake's western edge, leaving thousands dead and entire communities displaced. This persistent conflict has rendered any scientific monitoring on that side of the lake nearly impossible. Gas levels, particularly carbon dioxide and methane, remain unchecked in this ungoverned zone, heightening the risk of a catastrophic event. In contrast, the Rwandan side of the lake has seen more stability and is equipped with a robust system of monitoring for gas buildup and seismic disturbances. Rwandan authorities have recognized both the dangers and the opportunities posed by the lake's immense stores of dissolved methane. Methane is a highly combustible gas, and Rwanda saw a chance not only to reduce the risk of a deadly gas eruption, but also to harness this resource for desperately needed energy. In 2008, a small-scale pilot project was launched to extract methane from the lake's depths and convert it into usable electricity. By 2015, this initiative evolved into a much larger venture known as KivuWatt. Operated by a British-owned private firm with the Rwandan government's approval, KivuWatt invested $200 million to establish an advanced extraction and processing facility along the lake's eastern shore. The system works by pumping methane-rich water from deep within the lake, separating the gas from the water, and then channeling the methane to onshore power plants. Once the gas is removed, the now safe water is re-injected back into the lake's depths. This dual-purpose operation helps stabilize gas levels in the lake while supplying electricity to the national grid. Currently, KivuWatt provides approximately 26 megawatts of electricity, which accounts for nearly 9% of Rwanda's total energy supply. Future plans aim to quadruple that capacity, potentially fulfilling a third of the nation's power needs. Yet, while the promise of methane extraction appears to offer hope, not all scientists are convinced of its safety. At the present rate, KivuWatt's operations are projected to eliminate less than 5% of the lake's total methane reserves over the next quarter century. Critics warn that these interventions, if not carefully managed, could destabilize the lake's delicate stratification. There are fears that the mechanical disturbance from gas extraction could puncture the thin barrier that separates the gas-rich lower layers from the upper water column, potentially triggering the very kind of limnic eruption the project seeks to prevent. Other researchers argue that the long-term effects of these operations are still unknown and might not surface for decades. The risk, they suggest, may outweigh the immediate benefit. Conversely, supporters stress the urgent need for energy in Rwanda and defend the project as both a humanitarian and economic necessity. In a region with limited access to reliable power sources, the ability to tap into Lake Kivu's natural gas could be transformative. Yet the lake's serenity is deceptive. While Lake Monoun first revealed that limnic eruptions were possible and Lake Nyos tragically demonstrated their lethality, Lake Kivu remains an even more ominous threat. With millions living along its shores and violent conflict ongoing, it stands as one of the most potentially catastrophic natural disasters on Earth, quietly simmering beneath the surface. Whether or not such a disaster ever materializes, the sheer scale of what could happen places Lake Kivu in a category all its own, a silent, deadly giant whose true danger is not if it will awaken, but when. If you found this video insightful, please give it a like, share it with others who need to know, and don't forget to subscribe for more deep dives into the world's most mysterious and dangerous natural wonders. Stay curious and stay informed.